Okay, good morning, everyone. Oops, what's wrong with this? What happens to this projector? Sorry, the projector seems not working. Okay. 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 Thanks. Sorry for the problem of the projectors. So, okay. So, in the last lecture, we walked through the um, perception algorithm, explain why their updating rule makes sense. And then we talk about like some theoretical guarantees about perception, right? So basically, the behaviors of perception can come two types of behaviors. And one type is that, okay, if your data is linearly separable, then it will guarantee it will converge to some separating hyperplane, which separate out your positive examples from negative examples perfectly. So that's a good thing, right? So basically, if your data is linear separable, you only need to make a finite number of updates. Then you're gonna find a separating hyperplane, which correctly classify every training example. So second type of behavior is when your data is not linearly separable, then your perception is not guaranteed to converge. Instead, if you just keep running it, keep pathing the sequence of training examples onto perception algorithm, and eventually it will enter an infinite loop. Like basically, you're gonna cyclically update a set of vectors, weight vectors, but keep cycling, and not never end, right? And okay, so then we'll mainly focus on the behavior when the data set is linear separable, because in the practice, we're not gonna run perception for infinite number of iterations, right? We found out, okay, if this data is not linear separable, perhaps we just run like 200 iterations. We're gonna stop. We're gonna enforce it to stop, right? So that's not a big issue, right? So the issue is that, okay, if your data set really linearly separable, how many updates would a perception algorithm make at most? That comes to the so-called mystic bound theorem, right? We just gave a quick review about mystic bound theorem as we discussed in detail in the last lecture, right? So the takeaway from mystic bound theory just tells us that suppose we have a binary classification data set with n-dimensional input features, right? If the data is linear separable, then perception algorithm will find a separating hyperplane after making a finite number of mistakes. So remember, perception only update when it makes mistakes, right? So number of mistakes actually is number of updates of the model. But if you look into the detail of theorem, it's not only just saying, okay, find a number of mistakes, actually give an upper bound of mistake, right? So, so basically, if we assume we have M training examples, right, and every input vector has a dimension n, and every feature vector or input vector its norm is bounded by R. So imagine there's a radius, right? There's a circle or sphere which contain all your input vectors in your training set, right? And then suppose this data set is linear separable in that there exists some unit vector. By unit vector means like norm of the vector is 1, such that this hyperplane determined by U has margin gamma. So what's the definition of margin? Yes, exactly right. This is a very important concept. That's why I'm asking, right? So margin is for a hyperplane means that, okay, among this data set, the closest data point to this hyperplane, what's the distance, right? So this is called margin, right? And we assume that, okay, this data is linear separable, and then we pick up a hyperplane, separating hyperplane, right? Which represented by unit vector and also the margin gamma. Then we'll claim that the perceptron algorithm will make at most square of R over gamma mistakes on the training sequence. Right? It doesn't matter how you're gonna stream your training sequences into your perceptron algorithm. No matter how you're gonna do that, the number of mistakes, or in other words, the number of model updates perceptron will make is at most this many. Right? So I'm showing the ways of proving this, right? So basically, we have 3 steps. I'm not gonna go to this again, right? But basically, we have 3 steps. The first 2 steps are proof using induction method. We show that, okay, after T mistakes or updates, we have this dot product between U and your current model weight vector WT is no less than T gamma, and the square norm of WT is upper bounded by T times R square. Then you just, third step, you combine these 2 inequalities using Cauchy-Schwarz inequality, and then you solve this connected inequality, left hand and right hand, in terms of number of mistakes T, and you get this bound. Right? That's the idea, right? So we hope you can replicate this proof manually after the class to strengthen your understanding. Right? This is the only theory we strongly require you to know every detail, right? In our class, right? Okay, so we also gave a geometric explanation of this bound, right? So imagine you have a data set like this. You have a positive examples here, you have negative examples here. Obviously, this data set is linearly separable. So that means, according to our theorem, you run perception after making a finite number of updates or mistakes, you eventually find out separating hyperplane, right? So how do we bound the number of updates or mistakes? Right? So first of all, we're gonna find out a radius such that the sphere with that radius will cover all the training instances, right? So that radius actually is upper bound of the norm of each feature vector, right? So remember, the norm in a feature space or instance space actually represents some kind of length, right? So basically means like, okay, the distance between every feature vector, which is point, right? And the origin, this distance or this length will be no larger than R, right? And meanwhile, because this data set is linear separable, so we can pick up arbitrary separating hyperplane whose weight vector is a unit vector and the margin is gamma. Then we'll claim that running perception, the number of mistakes you made is at most R square over this gamma square. Right? Any questions so far? Yeah, you might ask, like, that means like we probably have many bounds, right? Yeah, the answer is yes. So as long as your data is linearly separable, you can draw any separating hyperplane, right? And when you update, when you normalize the space vector as a unit vector, you have a corresponding margin gamma, right? And then use that to construct upper bound. Okay. Does it make sense? I can draw another. I can draw another line. Yeah, the gamma is the minimum distance between the data points in this data set and the hyperplane. Means the line here. How do you know this is necessary hyperplane? Separating this No, here we're just assuming a hyperplane because we're talking, because the perceptron algorithm itself is just trying to find out a hyperplane because the linear model, right? Remember, it's linear model. If you look at the classification boundary, it's simply W transpose X equals to 0, right? And X is, of course, is augmented with 1, so W has some bias parameter inside, right? But basically, your classification boundary with linear classifier will always be a hyperplane, right? And this is the goal of perception. You just want to find out a hyperplane, not to find a quadratic surface or more complicated surface, not like that, right? Okay, any other question? The radius squares? Yeah. Yeah, it comes from here, right? Yeah. So our precondition is that your norm of each feature vector is no bigger than R, right? Is the upper bound of your length, right? And you have some like a separating hyperplane, whose margin is gamma. Of course, in the case that your width vector is unit vector, then we can upper bound the number of mistakes as R over gamma squared. Yeah. So the point I want to make is that, so basically for any separating hyperplane for this data set, from its margin, you can construct a mistake bound, right? So you can imagine there could be a lot of different upper bound, right? So then among those upper bound, right, which one is the tightest? Or using which hyperplane will give you the tightest upper bound of the number of mistakes? Well, taking average is one way, but it's not find the tightest bound, right? Yeah, minimize the bound. And under when do you get this minimum of the bound? Yeah, when the margin is maximum, right? Yeah, if you want to find the tightest bound, you want to look at which separating hyperplane will give the largest margin, right? That is tightest bound. And this margin corresponds to the margin of the data set, right? What's the definition of margin for data set? Right? Margin for data set means that if you look into all possible separating hyperplanes for this data set, you're going to pick up the one who has the largest margin. That margin is defined as the margin for the whole data set, right? It's an indicator of how easily or how separable your data set, right? Does it make sense? Right? Margin for data set. Remember, when we talk about margin, we brought up two definitions. One definition is the margin for a particular separating hyperplane. That is, what's the distance between the nearest data point and the hyperplane, right? And then we generalize this concept to the margin for the whole data set. So for linearly separable this there could be like infinitely many separating hyperplanes, right? Then we're gonna look at, okay, which separating hyperplane will give the largest margin. Then we use that margin as the definition of the margin for the whole data set. Does it make sense? Right? And this margin for the data set actually indicates the separability of the examples in this data set, right? The larger the margin means that the easier the data can be separated, right? So also can use that to get our tightest upper bound of the mistakes. Any question? Yeah, gamma is the margin. Okay. So now to strengthen our understanding about this mystic bound, we want to do a little bit exercise, right? We want to estimate the mystic bound first, learning a simple family of linear classifiers, right? So let us consider we want to use perceptron algorithm to learn a function called disjunction, right? A disjunction of n variables, right? So remember, disjunction is a Boolean function, right? This is disjunction function, right? Y equals to this, okay? And as we discussed previously, this kind of like Boolean function can be well represented by a linear classifier, right? We can construct an equivalent linear classifier for this Boolean function, right? So the question is that, okay, suppose I have collected all the instances for this Boolean function, meaning that, okay, I'm giving you all combinations of the values for x1 and xn to xn, and also y values, right? You threw them into your perceptron algorithm. Then how many mistakes at most would your perceptron algorithm make before it finds out a separating hyperplane or equivalent linear classifier to that function? Does the problem sound clear? Right? So then we can use mystic bound theorem to give some kind of estimate, right? Right. To apply the mystic bound theorem, just talk about, right? So consider we need to first make clear our training data set. So our training data set consists of all 2 to the power n Boolean input feature vectors, right? Remember, x1 can take true or false, x2 take true and false, xn take true and false. So you have in total 2 to the power of n input feature vectors or training instances, right? Yeah, yeah. And to apply our bound, right, we need to know what is R and what is gamma, right? And once you know what is R, what is gamma, and then just apply this, right? So first question is, what is R? So remember, R is upper bound of the length of the input vectors. Is 1. Is 2 to n. Right, remember the length, what is the definition of length of a vector, right? No, what's that? Yeah, you're gonna have n features, right? Your n elements, your feature vector, right? And now you want to look at what is the maximum norm or maximum length of your feature vector. What's that? Just 1? Think about that. Think about that. Square root of n. Yeah, it's close, right? But you forgot to add a constant feature, right? Right. So remember x1. So let us consider a feature vector here, right? So it's x1 to xn, right? Right. Each element is either 0 or 1, right? If you want to look at what's the maximum length of this vector, right? You will see that we'll take all elements to be 1, right? That comes to the longest feature vector, which is length, which is n, right? Which is sorry, it's square root of n, right? But here, remember, we're using simplifying notation, meaning that we're augment our feature vector with a constant feature 1, okay, to account for the bias term. So our augmented feature vector will be x1 to xn and with additional constant feature 1. So if you look at what's the maximum length of this augmented feature vector, this is just a square root of 1 plus n. Y applies to 1. Yeah, okay. So remember, the full linear model is something like this, right? Right, you got W transpose X plus B, right? So here, for simplifying the notation, we're gonna introduce an augmented representation, right? So we're gonna augment X with constant feature 1, and correspondingly, we're gonna augment our W with bias parameter B, right? So then you have this augmented weight vector, you have this augmented feature vector, and then your classification score is just represented as dot product between these two augmented vectors, right? So here we're talking about, because all the theorem are building upon the augmented representation of the linear classifiers. That's why we need to append 1 our feature vector. Any question? Yeah, hopefully everyone feels comfortable, but if you don't feel comfortable, never mind, just spend a few more minutes after class and to look into this, right? Okay, so the first step is done, right? We have found a upper bound of the norm of the feature vectors across the entire training instance space, right? So next, we need to find out a separating hyperplane and pick up its margin gamma, right? And then we can use that gamma to construct our mystic bound, right? Okay, so that will lead us to our previous discussion, right? So we talk about, okay, if we look at this disjunction function, right? How do we construct an equivalent linear classifier? A very straightforward way is to look at when this disjunction function is 1, right? We know that as long as there is one input variable to be true or 1, right? Then disjunction is 1, right? Equivalently, that means if and only if the summation of these n variables is no less than 1, your disjunction function is 1, right? And then we can construct a linear classifier accordingly, which is just x1 plus x2 plus xn until plus xn minus 1 equals to 0, right? That's how we give an equivalent linear classifier to represent this Boolean function before, right? Now, my question is, can we use it to get margin and then use the margin to construct our mystic bound? Can we? Yeah. Yeah. Right. So then the question is, what's the margin of this linear classifier? with respect to this data set. Yes, yes. And according to that definition, what will be the margin for this classifier? What's the minimum distance between the whole, every data point, this whole data set, and the separating hyperplane represented by this classifier? Y is 0. Right. Right. That's a very acute observation. Right. Unfortunately, we cannot use this linear classifier because the margin is 0. It's pretty easy to check. Why? Because you can pick up any training instance where you just set one element to be 1, right? All the others to be 0. Then you see the left-hand side is 0, right? Geometrically, it just means, okay, that data point stays right on the hyperplane. Right? Does it make sense? If that data point stays on the right, stays exactly on this hyperplane, what does it mean? It means the distance between that data point and the hyperplane is 0. Right? And then what's the margin? Margin is simply 0, right? Right? So because the margin is defined as minimum distance between every data point and the hyperplane, right? Now you have a 1 point stay right on the hyperplane, then the margin is 0, right? That means, like, okay, if you use this margin to construct upper bound, right, which is R over gamma squared, this upper bound is just infinity. Okay? That isn't wrong mathematically, but it's not meaningful at all, right? Because everything is less than infinity. Okay. Does it make sense? Any question? Okay, so that means, okay, looks like simple intuitive hyperplane we constructed are not good because it has the 0 margin, and the bound constructed from the 0 margin is not much valuable or useful, right? And then what's our strategy? We need to find out another linear classifier with non-zero margin, right? And as long as with non-zero margin, we know that the bound won't be infinity, right? And they have a meaningful bound, right? So there could be a lot of choices. Remember, when your data set is linearly separable, you have infinite many possible classifiers which can separate them out, right? We just happen to choose one which pass through data points in a data set which gives you 0 margin, right? But now we just move this a little bit to make sure no point is gonna touch the hyperplane. Then we'll find out a hyperplane with non-zero margin. Does it make sense? Right? So here, what I give here is just move this hyperplane a little bit. I change my hyperplane to be summation from x1 to xn minus half equals to 0. Remember, from our intuitive construction, we're going to subtract the summation by 1, right? Now we're going to subtract the summation by half. So basically means I'm going to move this hyperplane along, the n+1's dimension by half, right? So it's just a parallel movement. Yeah, it's up to you to check. Yeah. Here I just give you one option. You can pick up any other. And the dot, what you're saying is correct, but I never checked. I will leave there as your task to check them. But let us first look at this simple one, right? So if we move this hyperplane a little bit, so that we get this hyperplane, right? And let's see whether we'll have a 0 margin. What's the margin for this new hyperplane? 1/2. Why? Mhm. Yeah, exactly, right? So you just need to look at under which configurations of those n variables you're gonna have the largest left-hand side, right? That corresponds to distance, right? So you have two possible choices which can make you to arrive at the minimum. First, you can set one variable, all of these n variables to be 1, all the others to be 0. So you got 1/2, right? Or you can set all x1 to xn to be 0. You also got 1/2, but it's -1/2. It doesn't matter because the distance is just take the absolute value, right? Take the absolute value of the left-hand side, right? In case you don't kind of like forgot the formula of calculating distance, right? It's something like this, right? Takes the absolute value and denoted by a norm of the weight, right? If you want to look at the minimum value, minimum distance, you just need to look at under which choice of x your numerator will be minimum. In this case, you can either make all x to be 0, or you can set one variable to be 1, all the other variables to be 0. In both cases, you're going to arrive at the minimum distance. Okay? And then we can conclude that, okay, we won't have a 0 margin. And the margin is actually, because no points will lie on the boundary, right? And the margin will be 1/2 divided by the norm of the weight vector, right? Okay. This is the formula to calculate distance. Then we got our gamma, right? Any questions so far? Yeah, that's a good question. Yeah, that's a good question. I think there could be maybe there is some like extreme case. Yeah, there might be some extreme case that you have that, but in practice, as long as your data set is linear separable, it usually corresponds to infinite many possible hyperplanes. Unless you want to construct a very, very extreme case. Yeah, yeah. You're gonna consider the position of hyperplane and angle, right? You want to rotate it, you want to move it, and to find the best one you believe, right? And later we'll talk about what kind of positions will possibly give you the best performed linear classifier. But up to here, I hope everyone is on the page, right? Everybody's on the page, right? We are trying to find out a separating hyperplane with non-zero margin. So that basically means no points should stay on the margin. So we can calculate the minimum distance, which is non-zero, right? And then your margin, once you're given, and then you can just apply the Misty-Bound theorem to get the bound. Any questions so far? Okay, again, if you don't feel comfortable or you feel like didn't catch up, it doesn't matter, because this calculation is pretty straightforward. Please spend additional time after class to look into the slides and to get to our point, right? Get our discussion why we would like to move the hyperplane. The reasons that we don't want to have any points to lie on the boundary to give you zero margin, right? Because zero margin will give an infinite bound, right? That doesn't make any sense. Okay, so we hope that throughout this a little bit theoretical discussion, we need to know, you can understand what's the mystic bound from perception, and what's the strategy to prove this, and how do you apply this bound to give some like rough estimate of the number of updates for perception algorithm. Okay, so the remaining items about perception is the practical variance. So in practice, although the algorithm we have introduced, right? So but in practice, people always invent different variants to adapt to real world problems, right? So here are several practical variants we would like to discuss. So first, in practice, when you have a finite data set, what's the standard recipe to execute perception algorithm? Then we're going to talk about the two variants. One is called margin perception, and you see that margin perception tries to find out a hyperplane with at least some kind of margin. Okay? We'll see why. Okay? And then we'll talk about weighting and averaging perception. That is to deal with non-linearly separable data set. Right? As we mentioned, like in theory, if you just keep running perception under some like non-separable, non-linearly separable data set, it won't stop. It will enter into an infinite loop, right? So in practice, we have to stop at certain number of iterations. But then how do we make our perceptions to be as robust as possible? So that leads to the so-called weighting and averaging perception. Okay, so first, the standard algorithm to implement perception in practice. Right? So because in practice, we're always assuming our data set is finite, right? And you can't guarantee that just passing through the data set once, you're gonna make your algorithm to correctly classify every example, right? So perhaps you have to pass through the data set multiple times until you correctly classify every example that you don't need updated model anymore. So to do that, we usually run the so-called epochs multiple times. Inside each epoch, we random shuffle the data. Then we go through each training example according to the shuffle order, and then do the perception update when necessary. And after finish one pass of data set, we say this is one epoch is done. Right? And then we go to the next epoch. That means we're going to reshuffle the data and then sequentially pass through the example and look at if you make prediction, if your prediction is correct or not, right? If it is wrong, then you update the model. Just keep doing this for multiple epochs. So this is like standard practical implementation of the perception algorithm. And you're gonna follow this framework to implement the perception algorithm in the homework 3. Yes. Any question? Okay. So here, two things we would like to mention. First, how many epochs should we choose? Right? So this T is a hyperparameter to the algorithm, and it's decided by you. Right? It's decided by the users, and also is also related to the particular problems run. That means like you're gonna manually tune these hyperparameters. And second one, you see that we now use this trick to test whether you make correct prediction or not, right? We just multiply the ground truth label yi and your classification score and look at the product is non-negative or not, right? If it is negative, then you make a wrong prediction, then you update the model. Okay. Oh, before we proceed to margin perception, any questions so far? It is possible, but eventually you're gonna correctly classify every example. Yeah. The number of iterations. What do you mean by number of iterations? Yeah, it's possible. But the theory tells us even you count that updates, right? For updating, because you, for example, this time you classify this example correctly, next time wrongly, you're gonna update twice, right? Or third times, right? But the total number of updates, no matter you're gonna repeatedly making mistakes for a single example, will be upper bounded by that bound. Yeah, it won't exceed that bound. Any other question? Okay, so now let us move to the first version, first variant of the perceptron. It's called margin perceptron. Right? So it was motivated by the question that suppose your data set is linearly separable, right? So as we mentioned, like, it could be many, many separating hyperplanes, right? So here we give this pile of positive examples, this pile of negative examples, right? I just randomly draw two hyperplanes, right? And it looks like H1, H2 both perfectly separate positive from negative examples, right? Now, if you were the user, which one would you like to use? Or which one would you prefer? H1? Why? There is more balance, right? But why being more balanced seems safer, seems more performing better in the generalization? What? Larger margin. Yeah. Then the question is why a larger margin is better? Yeah. Why a larger margin tend to give us better prediction for, say, some unseen future examples? Yeah, it appears to like related to the distribution of the data, right? And seems like the more the farther away of your classification boundary from those data instances, the safer of your classifier, right? This is our intuition, right? But we need a little bit more analysis. So why we choose a classifier whose boundary is closer to the data will lead to more mistakes potentially. So this relates to how you're gonna, how those positive examples and negative examples are distributed. Right. So imagine when you collect the data set, right? When we collect data set means that, okay, we draw samples from the underlying distribution of the data, right? The data distribution, as we mentioned before, is usually is super complicated, right? But if you draw samples from the data distribution, the collected samples are likely to stay on the high density regions, right? Does it make sense? You draw a sample from a distribution, of course, those samples will more likely to appear or come from the high density regions of the distribution, right? So if you have a small margin, what does it mean? If a small margin, that means your hyperplane is easily passed through the high density region of the data, right? Right. So like H2 here, it passed through the high density region for positive examples and high density region of negative examples. So if it's high density region, it means that, okay, it is likely surrounding this hyperplane, there appear some examples, right? That come out some examples, right? And that come out some examples, right? If that examples show up in the opposite side of the boundary, you're gonna make mistakes. Does it make sense? Right? You have a, that's because you have small margin. You have a small margin, that means your classification boundary is getting close to the high density region of data samples. Because of high density regions, you can imagine there could be a lot of random examples, like random negative examples, show up on both sides of the hyperplane. Right? And according to our hyperplane, on one side, you are making correct prediction, but on the other side, you're making wrong prediction. Right? So here, for example, H2 here, right? When it passes through the high density region for positive examples, so you can imagine on those red shaded area, you have a lot of positive examples. Right? So you have a high chance that many mistakes, a lot, right? And similarly, if you look at H2 pass through this high density region of negative examples, which we roughly draw it as a green ellipsis, right? Shaded green, right? So you can see, because high density regions, you can imagine many negative examples can appear on both sides of H2, right? And of course, on the other side, H2 will make a lot of mistakes. That's why in general, if you apply H2 to some future unseen examples, you potentially can make a lot of mistakes, because many high likely or many examples with large probability will show up on the opposite side of the boundary, which lead to classification errors of H2. Does it make sense? Right? Any questions so far? So now let us contrast the two. A classifier with larger margin, right? Like H1. H1 has larger margin, meaning that H1 is kind of far away from both positive examples, negative examples, right? So that means H1 is more like to pass through the low density regions for both type of examples, right? Then you can imagine like the chance you will get the negative examples here is very low, right? Or the chance you have a high chance you have a positive examples showing up here is very low as well. That means the chance or the possibility your classifier H1 made a mistake is much smaller, right? That's why we should prefer large margin classifier, right? Because it passes through low density regions, and low density regions means that less likely that some examples show up surrounding your hyperplane, and less likely your classifier make mistakes. And later we will talk about generalization error bound. Those can be showing more mathematically, more quantitatively, to give you a sense why large margin will better. You'll see that large margin classifier will give a larger, a better generalization error bound. Okay, now that we should encourage our linear classifier to have large margin, right? And then in the perceptron algorithm, can we at least ask our fine classifier to have some kind of margin, right? So this is called margin perceptron. So what is margin perceptron, right? So it just changes the updating rule of the perceptron algorithm. We're gonna pick up a positive eta, right? This eta sets the threshold of the margin for our linear classifier. Then every time, as long as this guy is less than eta, then I will update my model. So in the standard perception, we know that we update our model when we make a mistake. That basically means yi w transpose xi is less than or equal to 0, right? In this case, we make a mistake. Of course, we need to update our model, right? But in margin perception, as long as this inequality holds, we're going to update our model. So what does this inequality mean? First, if your prediction is wrong, we'll certainly update the model, right? So that it actually keeps the behavior of the original perception. But more than that, even my product of yi and w transpose I is bigger than 0, we still are possible to update our model. In that case, this condition just means your distance between the data point and your current model, the separating hyperplane, is less than eta. I still need to update the model. Right? So remember, the left-hand side is the distance. Is the distance between xi and the width vector w, right? The separating hyperplane. So that basically means, okay, I'm not only requiring my model to correctly classify every example, but also the distance between every example and the separating hyperplane is at least eta, right? If it's less than eta, you have to re-update the model until you got a enough margin, which is at least eta. Does it make sense? Right? So that's the idea of margin perception, right? Why? This is a good idea because through this change of the algorithm, we can intentionally set a relatively large margin if we want. This setting comes from the eta, right? And there also comes some downside, right? What if your eta is too large and even larger than the margin for the whole data set? Then what will happen? Yeah, you'll never converge, right? You'll never converge because you won't be able to find out a hyperplane which that large margin, right? It beyond the limit of the data set. Right? Any questions so far? Oh, yi is not Boolean value. Yi is either 1 or -1. Okay, xi here is not Boolean vector. It's just a general feature vector. Yeah. So this is not the case we discussed like learning a Boolean function. We're talking about the general case. Your x can be actually like real valued feature vector. It's not equal y, because w transpose xi is a real value, right? Real valued score, and we use the sign of score to determine our prediction, right? So if you make a correct prediction, that means your score and your ground truth label will have the same sign, right? That's why their product must be positive. Otherwise, you're making wrong prediction, right? Another question? Okay, so next we're going to talk about let's talk about the case that your data set is actually not linearly separable. Right? This might be the more common scenarios, right? You can't imagine your data set is so good that it can be simply represented or classified by a linear classifier, right? it is possible that, okay, most of the examples your data set is linearly separable, except a few outliers, anomalies, so on, right? You can't throw up your perceptron or linear classifier just because several hard to classify examples, right? Then a natural idea will be, okay, we want to retreat to the case that, okay, why don't we just find a linear classifier or separating hyperplane with minimum mistakes on the training set? Now that your data set is not linearly separable, I'm just trying to find out a separating hyperplane has few mistakes, as few as possible. Right? This is the reasonable request. Unfortunately, finding a hyperplane with minimum mistakes is NP hard. So that means it's very, very hard to get. Right? So natural idea will be, okay, looks like find a single hyperplane, the optimal hyperplane with the minimum mistakes is not realistic. Then why not we construct a collection of linear classifiers? Okay. During the running, you see that we're always trying to adjust the position of our hyperplane, right? And through the history of the running perceptron, right? You can pick up all those hyperplanes and look at which one has, look at everyone, like how many mistakes you have made, right? And of course, the more mistakes you made, the less important for that linear classifier, right? But the few mistakes you make, the more important of classifier. Then we can aggregate all those collection of classifiers together to make our prediction. So this is like ensemble learning. Does it make sense? Right? So this comes to the so-called vaulted perceptron. So basically, vaulted perceptron tries to track every distinct separating hyperplane, not separating hyperplane, every distinct linear hyperplane during the training, right? But meanwhile, I'm gonna look at what's the life cycle of that hyperplane, right? Remember, as long as we make a mistake, we're gonna update the model. That means the life cycle of that hyperplane is over. We're gonna update it and come to another hyperplane, right? So then the length of this life cycle indicates the quality of the linear classifier, right? The longer the life cycle it is, meaning that, okay, the more training examples that classifier can correctly predict, meaning that, okay, it is more reliable. So we just count this life cycle. So let's see the procedure, right? So the whole framework is the same, right? We initialize our weight vector to be 0, right? And then we're gonna use a variable m to record the life cycle for every distinct hyperplane, right? How can we do that? Go through every epoch, right? And then we'll go through every training example, right? If your current model can correctly classify the example, then I'm gonna increase the life cycle for that current hyperplane by 1. Meaning it survives for 1 more example, right? And we'll keep doing this until I make a mistake. If I make a mistake, that means my life cycle is over. And this CM record how long my current classifier has survived, right? And then I create a new classifier because I updated my model, right? I initialized my life cycle to be 1. Okay? And just increase the number of distinct classifiers M. Right? And if next example, my new classifier can correctly predict that example, I'm going to increase its life cycle by 1, right? Means it survives 1 more example. I just keep doing this until the new classifier mispredict the example. That means that life cycle is over, I create another new classifier and initialize the life cycle by 1. You just keep doing this. You can imagine after we finish the running of the perceptron algorithm, you have a collection of linear classifiers along with their life cycles, like C1, C2, C3, and so on. Okay. And those count, or also called life cycle, can be viewed as the vote for its prediction, right? And the longer the life cycle for a classifier has, the more vote or more important the prediction from that classifier. And eventually, our prediction will be made by the aggregated votes of the prediction made by every distinct classifier. So it's kind of similar to the boosting, right? We have a collection of classifiers, and each classifier has their own votes. And then during the final prediction, I will use every classifier to make prediction, and time is vote, right? And of course, positive, negative, minus, and we just compete between the total votes for positive prediction, negative prediction, and find which one wins. That's our final prediction, right? This is called vote perceptron. Any questions so far? Okay. Which one you mentioned? This one? R? Okay. R is the learning rate. Yeah, its learning rate is simply, in most cases, simply set to 1. Does it overfit training data? Yeah, it's some sort of overfitting training data. But right now, let us not consider the overfitting issue right now, because linear classifier itself is kind of resistance to overfitting, right? It doesn't matter like you combine a bunch of linear classifiers will kind of like make the situation worse. I don't know. Yeah, this is something I don't know. Yeah, but basically you can view it as a kind of like a ensemble learning approach, but it's not boosting. Remember, it's not boosting, it's not bagging. Right? It's just a way to create ensemble classifiers, and during the running of whole perceptron, just look at which classifier seems fit the training data better than the other. Use how many examples it can fit as your vote. Then you do aggregate prediction. And from our discussion about ensemble learning or boosting, we expect doing this is more robust, right? Yeah, doing this is more robust. No, I'm saying robust, meaning not mean like it is more robust than boosting. I mean, it is more robust than a single perception algorithm. Okay. And we'll talk about this is in the case that, okay, your data cell in nature is not linearly separable. The relationship is not linear, right? And then we're not talking about, okay, the data set is not linear separable because it is corrupted highly by high noises, right? Like if your data set in nature itself is not linear separable, then you fit it as a linear model. Then your model's capability will be limited, right? The expressivity will be limited by the model's own capacity. Right? So doing this kind of increase the capacity of your model. Right? But that's still like, okay, what if I add additional noises? Of course, you're doing this will make you better fit the data, right? And of course, it's gonna be influenced by the noises. Right? That's kind of like a trade-off. it's your model doesn't work well. Maybe you're overfitting data such that you overfit noise in data, or maybe your model is kind of like under expressive, right? It's not expressive enough. You want to increase the flexibility of your model. Any other question? Go to the first mistake and then on to the second mistake. Yeah, you can do that. This is just for simplicity, like for the implementation convenience. If you want to exactly track, because there's a little bit difference here, right? It's not like exactly the number of mistakes made. So basically, as long as you create a new classifier, right? You will initialize your count to be 1, right? And then you just as long as you make a correct prediction, you add the count by 1. And when you make the first mistake, then you stop, right? So basically the life cycle is 1 plus the number of mistakes. No, the successful number of classifications you made by your current classifier. It's not exactly the same as the number of wrong predictions you made. But if you want to switch to that, yeah, of course you can do that. But you have to imagine like, oh, you have to consider cases like, what if when I update the model, I still cannot correctly classify any example. For example, when I update this, right, I proceed to the next example, and I made wrong prediction, and then in that case, the life cycle is simply 0, right? You won't include that new classifier into your model list. Right? And in this version, well, it kind of like include every possible model during your execution of perception, even it doesn't correctly classify any example. Any other question? Yeah, because you're doing some linear combination of you're doing some combination of linear classifier, right? If you draw the classifying boundary, it's not linear at all, right? It's like it's like the horizontal and the vertical classifiers we mentioned as an intuitive example for boosting, right? So even for that simple examples, if you do a linear combination of their prediction results, that might give you a nonlinear boundary. This is the same thing, right? So again, doing this vaulted perception is trying to boost the expressivity of your linear classifier because you're combine a set of linear classifiers, right? And doing this just because we want to handle more complex data, such that just the linear classifier, just a single linear classifier might not be sufficient. Does it make sense? Any question? Do you see why is better than single perception? So you can imagine that your data, okay, if your data set is linear separable, that means your ground truth function is just linear. No need for this multi-perception at all. You just train linear classifier. That's it, right? But the question is that in many practical problems, your ground truth relationship is not linear. Right? You can't assume a linear model is enough to characterize the underlying ground truth function, right? And when it reflects in data, you will see the training data is not linearly separable, right? And then in this case, how do we extend the power or performance of our perception algorithm? One of the ideas is to use in this ensemble approach, right? I want to train a set of linear classifiers. I want to combine them together to boost my performance. Mhm. Yeah, yeah. You mean it's necessary to include those classifiers? Well, the empirical evidence shows it's necessary. Yeah, the reason is but this one is might be too simple, right? The reason is that if you look at when you combine those linear classifiers together, right? So if you look at the boundary of those classifiers, it could be quite nonlinear, right? So that means as it has the potential to capture the local relationship across different domains, right? Because every classifier, they only work for maybe just a subset of examples. So that means when your classifier is applied to that particular, to the examples surrounding that set of locations surrounding to that set of locations, you are doing correct, right? Now you just combine them together. You can imagine you're combining a set of classifiers, each working well for their own particular local region. You combine them together, you expect to improve the overall performance, right? That's the intuition here. That's why in practice, this is like effective way to enhance your predictability of perception. Any other question? No, no, there's no guarantee on that. This is just the practical approach, right? It's not like I want to show some error bound on that, like in Bootstrap. It's not like that. Yeah. Okay, the last thing we want to introduce the even simpler implementation of this idea, the ensemble idea, is called average perception. So for the votive perception, you see that we need to explicitly track every distinct classifier showing up during the execution of perception, right? And that means like if you run a large number of iterations, right? Someone pointed out, right? You might collect a large number of classifiers and their counts or life cycles, right? So this kind of be like memory intensive and could be costly doing this, right? In particular, if you're training with like 1 million examples, you don't want to record so many classifiers. So a very simple and easy approach is to use the so-called average perception. So the average perception doesn't explicitly record those classifiers. Instead, it just introduced another read vector. It's called A, right? And during the execution perception, no matter the current read vector updates or not, I'm gonna add the current read vector into A. Then after I finish running of all big T epochs, I return A as my model big vector. When we do the prediction, I use A to make a prediction. Like I simply apply a single linear classifier. What? Yeah, it is very, very popular. Oh, there's no guarantee who is better, who is worse. Yeah, you're just trying, but this one is working well. But this one is much easier to implement and much cheaply to run because you only have one additional weight vector, right? But during the execution, you can imagine that A is essentially doing a A essentially is just the summation of the count times or life cycle times every distinct weight vector, right? Because every time, no matter if your current weight vector survives, you can add into A, right? If it appears to be a new weight vector, it will add into A, right? So A is just the summation of all distinct weight vectors and their life cycles. So in other words, you can view like A has already doing some kind of aggregation of this ensemble of these distinct weight vectors. Then I use A to make prediction. So this is very, very popular. Okay, so let's stop here today and hope everyone enjoys your fall break and see you in 2 weeks. Yeah. Mhm.